Have you ever stopped to think about what makes a supercomputer, well, super? It's not just about being giant or costing a fortune. Nope, it's about a completely different way of thinking about and processing information. Today, we're going to peel back the curtain on the architectural magic that gives these machines their mind-bending power. So let's get right into it.
All right, here's our game plan. We're going to start with the fundamental motivation, this relentless quest for more speed. Then we'll crack open the processor's playbook and look at the special instructions that make it all tick. After that, we'll tackle a classic, real-world headache. What do you do with messy, scattered data? And finally, we'll look at the memory bottleneck and how these systems manage to keep their super-fast cores fed with data. So first things first, why? Why go to all this trouble to build these incredibly specialized, complex machines? What's driving this whole thing?
Well, at its core, a supercomputer is really simple. It's just the fastest computer you can possibly build at any given point in time. But its real value isn't just about the raw speed. It's about what that speed lets us do. Things like simulating incredibly complex systems to gain new knowledge, making problems that were once thought impossible actually solvable, and just massively speeding up the entire pace of science and engineering.
But here is the fundamental challenge, the thing that keeps engineers up at night. No matter how incredibly fast we make our computers, our ambition and the complexity of the problems we want to solve, from mapping the universe to curing diseases, is always one step ahead. We're basically in a constant race against ourselves.
And that race brings us to a huge shift in thinking, moving from scalar to vector processing. Now, scalar is the way your laptop probably works. It operates on one piece of data at a time. Think of a cashier at the grocery store, scanning your items one by one by one. Vector processing, on the other hand, is like that cashier hitting the single button that applies a 50% off discount to your entire cart all at once. The result? It's a game changer. We're talking huge efficiency gains, often delivering speedups of 10 to 20 times.
Okay, so we've got the why. We need these massive speedups. Now let's get into the how. We're going to open up the processor's playbook and look at the actual instructions, the plays, that make vector processing a reality. So, the most basic play in the book is the vector-vector instruction. Imagine you have two long lists of numbers. The processor yanks each list into a special, high-speed container called a vector register. Then it feeds both of those registers into what's called a functional unit, which is really just a fancy term for a dedicated piece of hardware that does math, like adding or multiplying. And boom! Out pops a brand new list with all the results practically all at once. And here's that same idea boiled down into a simple formula. Now, don't let the symbols freak you out. All this is saying is exactly what we just saw. Take vector I and vector j, do some operation on them, in this case multiplication, and then store the result in a new vector, vector k. That's it!
All right, the next play is the vector scalar instruction. This is what happens when you need to combine one single number, that's your scalar, with an entire list of numbers, that's your vector. A perfect example is converting a whole column of temperatures from Celsius to Fahrenheit. Part of that formula involves multiplying everything by 1.8. Well, this instruction lets you do that multiply by 1.8 step for the entire list in one shot.
And you guessed it, the formula makes it crystal clear. We're taking a single scalar value, s, and applying an operation to every single element in vector I to create a new vector, j. It's like scaling up your entire dataset with one simple command. Of course, all this lightning-fast processing is totally useless if you can't get data to the processor and get the results back out. That's where vector memory instructions come into play. You can think of these as the massive multi-lane superhighways that connect the processor's little high-speed neighborhood to the giant city of main memory. In this highway, it goes both ways. A vector load is the on-ramp. It moves a whole chunk of data from main memory into the processor's fast lane, the vector register. Then, once the math is done, a vector store is the off-ramp, writing all the results from the register back out to memory. Keeping traffic flowing on this highway is absolutely critical. So far, this all sounds great, but we've been assuming that our data is sitting in memory in a perfect, neat little row. But let's be honest, the real world is messy. So what happens when the data you need is scattered all over the place? This isn't just a small issue, it's a huge problem in a lot of real-world science and engineering. You know, imagine working with a massive data set where most of the numbers are just zero. That's called a sparse matrix. You don't want to waste precious time processing all those zeros. You only care about the important, non-zero values that are sprinkled randomly throughout memory. The solution to this is just brilliant. It's an instruction called gather, And think of it like giving your computer a personalized shopping list. One register, V0, holds the list of memory addresses, like aisle numbers, for just the items you need. So instead of going down every single aisle, the processor uses this list to jump directly to the right spots, gathering only the data it needs into a new, clean, organized vector V1.
And this slide just walks us through a perfect, simple example. Our index vector has the offsets 4, 2, 7, 0. We add those to a starting address of, say, 100, which gives us the exact locations we need to visit: 104, 102, 107, and 100. The processor then zips over to those spots, grabs the values, and puts them all together in a brand new, densely packed vector. It literally turns chaos into order.
And this brings us to our final and maybe most critical challenge. Look, you can build the fastest, most powerful processor in the history of the world, but if it spends most of its time just sitting there, twiddling its thumbs, waiting for data from memory, all that power is completely wasted. This is the infamous memory bottleneck.
I mean, the core idea here is you can't put a tiny fuel line on a world-class race car engine. It just won't work. The memory system has to be a fire hose, not a garden hose. The rate at which it delivers data has to match the processor's enormous appetite, creating a super high bandwidth pipe between the two.
One of the key tricks here is called S-access, or simultaneous access. So instead of one giant slow bank of memory, you have several smaller, faster ones working in parallel. It's just like having multiple checkout lanes at the supermarket instead of one single long line. While the processor is grabbing data from lane 1, lane 2 is already getting the next piece of data ready. By overlapping these cycles, you create this beautiful, continuous flow of data with basically no waiting.
And the next evolution of this is called C/access, which just takes this whole idea and kicks it into overdrive. Right? So if S-access was like opening more checkout lanes, C/access is like building a whole multi-lane superhighway leading directly to the store. It combines those multiple memory banks with multiple parallel data buses, creating this incredibly wide, incredibly fast path that's capable of feeding even the hungriest supercomputers out there.
So we'll end on this thought. The jump from doing one thing at a time to doing one thing to a whole list of data at once, that was revolutionary. It completely defined an era of computing. So the question we have to ask is, what's next? What does the future look like when computers can perform many different operations on many different lists of data, all at the exact same time? That, right there, is the next frontier in this endless quest for speed.